Okay, so let's look at some techniques for propositional unsatisfiability. So the simplest and probably it's not actually the oldest, but for some reason it is important because it is used in all logic programming systems. But so So we looked at the tautology checker, and one of the important things about the tautology checker is that at some point you had to compute the conjunctive normal form of essentially a big conjunction of formulae implying some other conclusion, right? I mean, so this implication, the rewriting of this implication into OR essentially means that your conjunctive normal form has to take this big and convert it all into OR, right, by De Morgan's law. So in that sense, this is actually quite a bit of effort for one thing, and it of course increases the size of the formula tremendously, right. So and anyway, finally when you looked at the tautology checker, it finally involved falsifying the argument, finding falsifiers, and then based on that deciding whether it is a tautology or not. So the falsifiability of the argument was an important aspect of that of the checker design. But if you look at something like this theorem, it's here you have this, take the second part. The second part is just a huge conjunction of formulae, right. So if you have all the hypotheses, you take all the hypotheses of an argument phi 1, phi 2, phi 3 etc. up to phi n, and you take the negation of the conclusion, that is not psi, and this psi is logically follows from this set phi 1 to phi n if and only if this huge conjunction is actually a contradiction or it is unsatisfiable, right. So since we had falsifiability as the cornerstone of the tautology checker, the natural thing to do is to look for unsatisfiability of this, and this huge conjunction has a certain advantage, and that is that if I am anyway going to use a conjunctive normal form, then having a conjunction at the top of a large number of formulae means that I can now apply a sort of a divide and conquer technique. I can just convert each individual conjunct into a conjunctive normal form. So which means I deal with smaller sized formulae, convert them into CNFs, and then the huge, we got a list of literals in our tautology checker, then that just means appending all the lists that we get together, right. So which means we just append all this, so you convert each individual conjunct into a CNF, that is a smaller problem. You essentially think of it as n small problems, and then you have to append all the lists to obtain the required list of literals, yeah. So in a certain sense, if you are committed to using a conjunctive normal form, the use of this theorem is likely to therefore be more time efficient than the use of a of the tautology checker design as we did before, yeah. Okay, so and that is in fact what actually resolution theorem proving does, right. So let's just quickly look at it as a propositional resolution, and so essentially what we are saying is therefore to show that some finite set gamma to show that a formula psi follows from a finite set gamma of propositions, we just show that the big AND of gamma and not psi is false, is unsatisfiable by first transforming this huge formula, the big AND and not psi, into a formula in conjunctive normal form. So, this we will of course represent this conjunctive normal form as a set of sets of literals. Okay. Normally in the form of while you are doing programming, it is usually as a list of literals, but we will look at it as a set of sets of literals, because essentially because of the idempotence of both conjunction and disjunction, duplicate occurrences do not matter, or actually the better thing to in order to reduce the size of the formula is to remove duplicate occurrences, right. Okay. So, supposing let this capital delta be the set of sets of such literals, where each set of literals is called a clause, and each clause in delta essentially represents a disjunction of literals, yeah, and the empty clause represents a contradiction, disjunction of literals, yeah, and the empty clause represents a contradiction. What is the empty clause? I mean, why is it? Why does it represent a contradiction? I mean, supposing I have an empty set. I have an empty set of literals. So what should it actually be? If I so now that I have gone from the language itself to just literals and sets of literals and sets of literals, then the question of interpreting what happens to the empty set in each case is important, right. So, what is the correct interpretation for the empty set? I mean, that's an important question, right. Okay, so supposing so let's look at this problem this way. Supposing delta is empty, that means there are no clauses in delta. What does this empty set represent? This is the standard thing in algebra is to take the identity element, right. So, delta actually represents a big conjunction of a collection of clauses, right, C1 to Cn. And what we are saying now, if this big conjunction, if n equals 0, then essentially you have a big conjunction of essentially an empty set of clauses, right. So, you obviously the identity element of conjunction is going to be the answer, right. This is standard, right, I mean everywhere. Let us go to arithmetic. The starting point of, let us say, summation. So, let us look at summation and products, right. The starting point of summation is the identity element, right. So, if I am doing a summation over an empty set of numbers, then the answer has to be 0, right. The point is this: if I take any set of numbers and I add a 0 to that set, I do not change the summation in any way, right, because 0 is the identity element for the sum. So, if I just take the empty set, that's just like having the set containing 0. So, the answer is going to be 0, right. So, if I were to take the empty product, all my product computations actually start with the identity element of multiplication. So, if I take the empty product, this is going to be equal to 1. What is the identity element of conjunction? Well, the identity element of conjunction is true, yeah, or if you like the brown one, yeah. So which means that if delta were empty, then this conjunction of delta, this conjunction actually gives me 1, right. However, supposing delta actually contained, supposing delta was non-empty, okay, and it contained some elements, along with it contained an empty set. Suppose, so this is the empty set of literals is also a member of delta. First thing, as any set inside delta represents a disjunction of literals. So, which means that this empty set, actually represents the identity element of disjunction, which is false, right. So, this has to be false, okay. So, if this is false, this delta represents a conjunction of a set of clauses, which means you are conjuncting with false, and false is a 0 for conjunction, and therefore, then this entire conjunction then becomes false. Is that fine? So that's what we, so if this set does contain the empty clause as an element, then you have already reached the contradiction. It does not matter what other clauses are there in this set, right. So this is what actually, the resolution uses, the fact that if you can somehow derive the empty clause as one of the clauses in your set of clauses, then you have already found a contradiction, which means all other clauses then become irrelevant, right. So this is what so let us look at propositional resolution, and we have, it is a good idea to look at all these algorithms from a propositional viewpoint, so that the extension to first order and other kinds of logics then becomes easy, because all other logics would have propositional logic as a sublanguage always in them. So these are very basic connectives, right, and, or, and, not, for example. Yeah. So okay, so this is how propositional resolution works. So the important thing is, so the techniques that we are looking at are, I mean, if you look at this, if you look at the truth table, I'm sorry. So if you look at the truth table technique, for example, so the main problem about the truth table is that it is not discriminating enough. I mean, you construct regardless of whether a certain atom is relevant or not relevant for the validity. I mean, even supposing this, even if this argument were valid, I can add a whole lot of nonsensical sentences to this argument, which do not have any connection with the atoms of this argument, and still the argument will be valid. Now, if I add all those nonsensical sentences with also their own atoms, then the number of atoms increases and the size of my truth table increases, and the construction of the truth table does not discriminate between what is a relevant atom and what is not a relevant atom, right, for the validity of the argument. Whereas what we would like to do in order to reduce the sizes of the sets of formulae and in order to speed up proving is reduce sizes reduce the number of atoms possible, or look at only those sets of atoms. So the falsifiability in the tautology checker was a way of looking at only the relevant atoms, right, which could provide a clue as to the validity or the invalidity of the argument. Similarly, in resolution, we are actually going to, so in resolution similarly, this is what is going to happen. So, it provides a directed way of looking for contradictions and using literals, and contradictions are easily obtained by looking at positive and negative literals. So, if there is some atom which occurs throughout the argument only in either positive form or only in negative form, then that atom is irrelevant to both, whether it is a tautology or it is a contradiction. That atom can at most make the entire formula that you create a contingent formula rather than, which means that depending on the truth of that atom, maybe it might be true or false, you know. So that atom becomes completely irrelevant. So all our efforts are actually directed towards trying to firstly reduce sizes of formulae, secondly using some directed approach which will focus on proving a contradiction or proving a tautology, right. And for that we require to essentially derive the empty clause, right. So essentially of course in general for any kind of propositional resolution, this is not particularly true of logic programs, but it's, if you can also use resolution as a theorem proving technique for any kind of arguments, right. So one thing is, so let's look at this finite set of clauses. So let's assume that delta is the finite set of clauses, and we have to just find out whether this set is unsatisfiable. That's what the problem of resolution, that's what theorem 4.3.2 gives you. I mean, I can just look upon a set of formula and ask whether they are unsatisfiable, whether they form a contradiction. So one thing of course is clear. So I have a number of clauses, and I might have two clauses C and C prime such that one is a subset of the other in this set delta. Now each clause represents a disjunction of literals, which means C prime, if C is a subset of C prime, then C prime represents a larger disjunction than C, which means C prime is irrelevant to proving whether it is a contradiction, right. So the entire clause C prime can be deleted, because whenever C is true, C prime is guaranteed to be true. Yeah. So, and since we are looking at this as C, so since these are two members within delta, it's like taking C and C prime, and C and C prime, where C is a disjunction of literals and C prime is a superset of C, is equivalent to just C, right. So it's not just that it preserves truth, it also preserves falsehood. So delta with this C prime removed is still logically equivalent to the original delta which had the C prime in it, right. Okay. So the first thing is that all such clauses may be deleted from delta, and of course we are looking at sets. If you are looking at lists instead, then as I said, you might have to put in an artificial ordering in order, because it's checking permutations. I mean, checking whether one list is a sublist of another without sorting them in some way, means it's essentially determining whether some sublist of the other one is a permutation of the first list, and determining permutations is quite complicated, right. So this is what I mean. So I mean, if I look at the problem of finding the median of a list of elements, I can do that in less than n log n. But if I look at the larger context in which I have to do such things, such operations also, then it's simpler to just sort the list. okay, and essentially amortize the cost of that extra factor that sorting gives over all the other operations that I might have. So, for example, list equality is very easy to check if they are sorted. I do not need to consider permutation. So, list equality checking is just linear, right. So, that itself is whereas permutations are actually n square or minimum of n square, right. So, okay, so that's a problem. So I can just delete such clauses C prime. The second thing is, supposing any clause C contains a complementary pair. After all, it's literals, so there could be a literal, there could be both P and not P in C. Since C represents a disjunction of literals, therefore the existence of P or not P makes all other literals irrelevant, and this clause C becomes true, becomes logically equivalent to true. If this clause C becomes logically equivalent to true, its presence in delta does not affect whether the clause exists or not. So, any clause which contains a complementary pair of literals can be deleted from delta without affecting logical equivalence, right. So, this is not something most resolution mechanisms tell you to do, but if you do not do this cleanup, very often you will slip up in your algorithm and not get a contradiction, or you will assume something is a contradiction which is not, because this complementary pair will allow you to derive something like an empty set, and whether that is an empty clause or an empty, whether that is an empty clause or the empty set of clauses is a question that you have to ask, because that's a huge difference between true and false, right. So we need to do this cleanup, though most works on resolution do not even refer to it, yeah. The third thing of course is that from the idempotence of and or, it is clear that all duplicate occurrences of a literal may be deleted from each clause. Okay. This also includes duplicate occurrences of clauses, because this is a subset or equal to, right. I mean, so you can delete duplicate occurrences of a literal from any clause without affecting logical equivalence. So this cleanup gives you a new set delta prime, which hopefully is smaller than delta, and of course what it satisfies this logical equivalence. So what we have done so far is that we have actually done a cleanup which preserves logical equivalence always. It is not usually true. Most derivations do not preserve logical equivalence, they usually preserve truth or satisfiability. But this cleanup operation alone, looked at in isolation, actually preserves logical equivalence. Okay, so yeah.
I can understand that if C and C prime are they consist of disjuncts and they are OR of many literals, then
Each of them is an OR of literals.
yeah. So how could we delete the superset?
Oh, okay. Because what we are saying is you have, so this, what we are saying is you have C which is, let us say, some literals L1 to Lm, okay, and you have C prime which is, let us say, L1 to Lm and let us say up to some Ln, okay. Then what you are, the fact that C and C prime both belong to delta means that you are looking at OR of C, OR of the literals in C and OR of the literals in C prime. Yeah. So if you are looking at this, then what happens is that this is just logically equivalent to L1 or Lm. Yeah. So that is just, so that is just equivalent to OR of C. Right. So I can delete C prime. So I mean the reason I am doing all this is because when I actually started doing some resolution proofs by hand, I suddenly found I was getting stuck at some various points, because these books do not mention that there has to be a cleanup done, there has to be this, otherwise you will be leaving irrelevant clauses and literals without being able, and you may not be able to derive an empty clause because you did not delete the irrelevant literals. Okay. So here actually in this particular case the entire clause C prime is irrelevant. If it continued to exist and you did your resolution and you may not get an empty set at all if you happen to do your resolution with C prime, right. And so you will be stuck, you will think actually that you could not derive an empty clause, and therefore the argument is invalid, which is a wrong assumption, right. So this cleanup is actually essential, though in actually programming it, many people just I mean it has to be just like nobody discusses sorting algorithms inside a tautology checker really. This cleanup is also never discussed really in any work that deals with resolution, but this cleanup needs to be done, otherwise you can actually get wrong results. Okay. Then the actual resolution method is I start with a clean set. Oh, by the way, this word clean, I just introduced it because I had to introduce a word. Yeah. So I start with a clean set delta. Okay, and so which means that, and I look at and I choose any atom. So a relevant atom is one which is an atom P such that there is a not P also somewhere in that delta. Okay. So let us look at all the clauses which contain P, okay, and let us call that lambda, and lambda bar be the set of all clauses which contain not P. So now you have already focused, you have already brought in your focus only on the relevant atoms. Only those atoms which have complementary pairs somewhere, both positive and negative forms somewhere in the delta are relevant. All other atoms are irrelevant, right. So any atom which occurs only in one form, either positive or negative, is irrelevant to resolution. So there straight away goes off here. So then again sorting the atoms, sorting the literals and so on makes sense, you in choosing such a thing. For example, if you use a sorting algorithm, if you use a total ordering in which the negation of an atom immediately precedes the positive version or immediately succeeds the positive version, then just looking through the list of atoms you know which complementary pairs exist in the entire set. Yeah. Okay. So now since delta is a clean set, first thing I take, so these sets lambda and lambda bar are subsets of delta. Okay. The first thing of course is that they are disjoint subsets because they are clean, because delta is clean. They have to be disjoint because any clause which contains P cannot contain not P. So the set of clauses which contain P is completely different from the set of clauses which contain not P. So this delta and delta bar are disjoint. But however, individual clauses C and C bar may not be disjoint. They might have some common atoms, for example, or some common literals. Okay. The other thing of course is that the C and C bar are mutually exclusive. as far as P is concerned. One of them contains P and the other contains not P. The one that contains P does not contain not P, the one that contains not P does not contain P. So, they are exclusive with respect to P. Once you have done that, so we do what is known as an operation called resolution on this complementary pair P not P, and that is a function. So, what do we do? It starts with delta. So, essentially we take these two sets lambda and lambda bar, and our resolution has to resolve on every C in lambda with every C bar in lambda bar. Okay. What is the and what does it do? So, which means that, and then what do? I take the unions of the sets after removing P and P bar from each pair of clauses. So, from each pair of clauses C and C bar, I remove P and not P and take the union. Okay. I do this for each pair C and C bar in lambda and lambda bar. So, what is the net result, net effect? I get a new set delta prime, but this set delta prime is not necessarily equivalent to the original delta. That is the first thing. Okay. What it does preserve is it preserves a satisfiability condition. Delta is satisfiable if and only if delta prime is satisfiable, and vice versa. Actually, since we are looking at a resolution method which is supposed to give you a contradiction, we are saying essentially that delta is unsatisfiable if delta prime is unsatisfiable. Okay. So, we are actually moving away from logical equivalence. So, the resulting delta prime, if you think of it as a conjunction of disjunctions of sets of literals, is not logically equivalent to the original delta. Okay. But what it does preserve is that if the original delta were unsatisfiable, this would also be unsatisfiable. This union tends to increase the sizes of clauses, and if for example delta had if lambda had k clauses and lambda bar had m clauses, the fact that you are taking all pairs C and C bar and performing the resolution, this last two, C belonging to lambda, C bar belonging to lambda bar, means that you are actually taking, you might actually be increasing the size of the number of clauses in the set delta prime. So, if you look at the cardinality of delta prime may not necessarily be smaller than delta in terms of number of clauses and in terms of sizes of clauses that are common, that are there in the two. But what other property does this have? Yeah, somebody said something.
One less atom.
Sorry?
One less atom.
That's right. What it does is it removes one atom completely from delta. So, if you look at, so this, since P and not P, this atom P occurs only in lambda and lambda bar, this operation of removing P and not P from all elements C and C bar, even though you are taking the union and you are taking all possible pairs of C and C bar, and therefore you might be increasing the sizes of the clauses, even though you are doing all that, the number of atoms, the total number of atoms in delta decreases by 1. So I mean that's crucial in order to show that this algorithm terminates. Okay. So in fact, so what you do is you start with a clean set of clauses, and while I have used the empty list here, okay, it could be the empty set. While the empty set does not belong to delta, if the empty set belongs to delta, you have got a contradiction already. If the empty set does not belong to delta and there is a complementary pair P prime in delta, P not P in delta, then what you do is you create a delta prime which resolves delta with respect to this atom P. The result of that is to give you a delta prime which is possibly larger, but it reduces the number of atoms by 1. And what you do is you clean up delta prime and call this delta and you iterate on this while, right. So, the fact that one atom gets removed in each iteration of this loop guarantees termination. So, what are the possibilities on termination? Either an empty clause appears at some point, in which case you have proved that your original argument is valid, or the empty clause does not appear, but there is no complementary pair left, so you cannot do any more resolution, right. If that happens, what does it mean? It means that since this new the new delta that you have got therefore is actually satisfiable, right. It is possible, since there are no complementary pairs, I can give some truth assignments to the individual atoms and somehow make the whole of this latest delta true, which means the same assignments can be applied to the original argument, the atoms in the original argument. And of course, in the process I have done various things to the various complementary pairs, but now it does not matter. Assign any truth value to those atoms which got eliminated and you have a satisfying assignment for the original argument, which proves that the original argument is invalid because you had negated the conclusion, right. So, right. So, this is what resolution does. It is important that, so this is the only, so this is actually the only proof of termination would be that there are only a finite number of atoms in delta and therefore this has to terminate somehow or the other. If in the process of resolution you remove one atom every time in every iteration of the resolution, you have to terminate. So, when you terminate, you either terminate with an empty clause as an element of delta, or you terminate with no complementary pairs available, in which case that also provides you your satisfying truth assignment to show the invalidity of the original argument, right. So basically you do not care what truth assignments are given to the atoms which were eliminated as complementary pairs, only the atoms that are left unresolved, a truth assignment to them will also give you a truth assignment to the original, will prove the invalidity of the original argument, yeah. Okay, so let us just quickly go, let us just quickly do an example by hand. So, here is some a data logic program which I thought I will just do. So, here is, so I will write it as a set of sets of literals, right. So, here is something. So, what we are essentially doing is, okay, I am going to take, this is too simple, so I will take a more complicated one. Okay, let us do this, yeah. So, let us take this. I have this set of sets. I am using small letters for atoms, B, E, not B, C, B, D, not C, D A D not A and then not D. Are you able to see all of this? So I have, yeah, so I have this. So essentially what I do is I choose any complementary pair. So one possibility is to choose this A and not A, okay, and I do a resolution on A. Nothing else has A in it, A or not A. So this is a single resolution with which will just give me this. So essentially what it will do is it will replace this set. I have to take this union without, so I get not C and D, right? That is what I get. So notice that D is common to both clauses, and of course this is a cleaned up version, right, since I am looking at sets, right. Of course now I can, so essentially this pair has gone. Here in this particular case the number of clauses is reduced, but and actually the sizes of the clauses is also reduced, but that is not necessarily true if I consider this pair. So if I look at this, I can do a resolution on B here, okay, and then I can do another resolution on B here. Okay. So what this will give me is a set EC, and what this will give me is a set CD, right. So now well, so essentially E and D are irrelevant, these are all, this is a clean set of clauses. So basically I have replaced these two, so I am actually already working towards termination in a very significant fashion. So I have only these three clauses, right. Now of which of course oh, there is a not D also, I am sorry. Okay. Now actually I have one possibility is of course to straight use D itself as a to resolve, in which case I have to do two resolutions like this, yeah. So both of these are on D, and this resolution gives me essentially not C here, and this resolution gives me C here, okay. And of course strictly speaking, so I actually have now three clauses, and strictly speaking I have to do a resolution with of both of these clauses with this clause not C. But however, okay, so if you were to do that, so essentially what you get is this derives the empty clause, and this derives, and this derives E, right. So you are left with essentially just two clauses, of which one of the clauses is empty. The fact that you have derived the empty clause essentially shows that this conjunction of disjunctions is a contradiction, yeah. And so that's, so it is important to realize that because of, I mean the empty set has to be an element of the delta. So your delta cannot be empty, firstly. If delta were empty ever, then of course it is already automatically true, right. So that is not something that's possible if you started with a non-empty set of literals. You would actually have to derive an empty clause, and this is an empty clause, right. So this empty clause essentially shows that you reached a contradiction. So so this so notice that if you were to take this formula and you were to take this, what is this? I mean, this is just false, right? Okay. It's true that they lead to a contradiction, but in general a resolution process does not preserve logical equivalence. Okay. Right. So that there is something subtle that is happening there. Okay. There is so this is but of course the main problem in resolution still is the fact that you have to compute a conjunctive normal form, and that can be actually quite expensive. And what we would like to do is look at methods which do not necessarily involve doing such conversions. So these conversions, especially using distributive laws, are very expensive. Okay. So something that does not necessarily use these conversions, these equivalences, which blow up sizes of formulae, is something that we require. And actually that's what happens with what is known as the Tableau method, right. So the interesting thing about the Tableau method is that it's a very symmetric sort of method, you know, and it also proves unsatisfiability, but without actually taking the formula, taking a huge conjunction, trying to compute conjunctive normal forms, nothing of the sort. So it just takes a formula. So essentially what we are saying is that we start with the formulae phi 1 to phi n, let us say. So essentially what we are doing is we start with the formulae phi 1 to phi n, and we have not psi. Okay. We have rules. Okay. The interesting thing about the Tableau method is that the rules are symmetric with respect to the underlying semantics that we have provided. So you take the Boolean algebra. It contains, it's actually, any Boolean algebra is also a complete lattice, and therefore lattices can be inverted. The principle of duality holds, and therefore it exploits that in order to the symmetry. So essentially, when you are looking at tautology and contradiction, tautologies and contradictions are dual concepts. There is nothing sacrosanct about either. So instead of focusing on just truth or just focusing on falsehood, you actually use both truth and falsehood in a way to derive your unsatisfiability result. So what actually the system has is that it has rules. So you take this language, you take the language of propositional logic, and you create a new meta language. Okay, you create a language on top of that, and the language on top of it just takes the underlying language and writes zeros or ones in front of each of these. So I am treating both So this meta language just consists of one prefix of 0 or 1 before each formula, right. So I am treating truth and falsehood symmetrically, and what we are going to do now is essentially we are going to look at conditions under which a formula is true and conditions under which a formula is false. Okay, and we are going to create a tree. No, remember that this resolution method is also a tree, right. Okay, so it creates a this branching structure and so on and creates a final node. So, this is like a tree, and the Tableau method is also a tree, except that the Tableau method has, just like the resolution method, it has a notion of consumption of a formula. Okay. Here look at this resolution. This clause not B or C is being used twice. That is what the resolution method wants us to do. All possible pairs C and C bar have to be resolved on a complementary pair, right. The Tableau method is more efficient in the sense that a formula is used exactly once. Okay. So, there is a notion of consumption in which once you have read the formula and applied a rule for that formula, you do not use that formula again. So, this fact, this is what makes Tableau somewhat more efficient than resolution. The fact that no formula can be used more than once in the Tableau method, that is an important aspect of the Tableau method. So, what we will do is and the second important aspect of the Tableau method is that it treats both truth and falsehood symmetrically, right, and it also creates a tree, but it has a notion of consumption of formulae, and once a formula has been consumed, it is never used again. Whereas most other proof systems actually might use a formula more than once, right. We will do that when we do the axiomatic proof systems, we will see that also. But the Tableau method is very interesting because it has this beautiful structure which is just, which uses both truth and falsehood with equal priority and comes up with what are known as closed tableau. Yeah. So, we'll define this notion of a closed tableau, and that a completely closed tableau is what gives you an unsatisfiability result, right, and we'll do that next time.